$1,000. It is very expensive. We want a device. We want a device which has to be in a very cheaper price. We want to standardize a protocol. We want to standardize our architecture design has to be in the way it can go and sit into the chip, which is like in constrained space, and the device which will work with a very lower power consumption. So, and the lifetime of the device has to be like in a years. Once I place a device, once I place a battery to my door lock, it has to work at least for 2 to 3 years. At least I expect for 1 year. If it is the battery power consumption is very high, and if the battery is getting to drain out very fast away, and no one will know, as a customer, no one will like to go and keep on changing the battery. That's like a very worst situation for a customer. He has to keep on monitoring before going out, and he need to verify either, okay, my door lock system is good or not. So that's the situation. So the device has to be very like a low power consumption. So this is the like a 6LoWPAN stack will offers with lower power devices, low data rate, and low cost devices. And there's the image that I have kept this from the Vele, the author, from Zach and Castin. So this is one of the very interesting book. So those who want, it's completely, the PDF is available in it. So if anyone can look into it, this is a first book on the 6LoWPAN, and it's very interesting. He took the way is very well from the point initial he took up, explained each protocols as well, layer by layer. So 6LoWPAN, yes, IPv6 came into picture, and now it's very much interesting part is how the 6LoWPAN, the IETF has came up with a 6LoWPAN, 6Low working group that is like an, I'm not sure how many of you are aware about an IETF. So let me tell about this IETF. IETF is one of the working body. So that is under the Internet Society. That body is called as like an Internet Engineering Task Force. So this Internet Engineering Task Force completely purely technical. So there is no like an documentation law, like an nothing as purely technical perspective. It completely works on programming. So they'll mention like the king will be the best programmers in the way. There's some quotation specific. So IETF working group, I have like a specific, so many different kinds of working groups in the area. It can be a routing area, it can be a networking area, it can be a security area. So based on that, in each different sector, even in the application layer as well, in the application area, so there are so many working groups out there. Even if there's a standardization is coming up, for example, transport layer security, new standardization came up, so 1.3. So who is going to contribute to it? For example, IPv6. So IPv6 standardization, who is making it? CBOR, or as like an the other security like an the specific like a 6LoWPAN. Who is contributing to it? Is it like a specific industry, or is it like a specific IEEE, or is it from like any like a non-profit organization? That's the one, IETF. So IETF is the one global organization. So it is Internet Engineering Task Force. It supports, it's like a completely work on the standardization of the internet protocol standards that can be like, as I mentioned, for in different layers. And also it is completely open for everyone. Anyone can work on it. So maybe probably some of you have referred an RFC, request for comments. RFC is a document. So that is like a Bible for the, if I want to 6LoWPAN, if I want to understand the 6LoWPAN, so then I will go through the 6LoWPAN RFC. That is like an Bhagavad Gita, the document is complete. It consists completely about that. So if any modifications has to come up, so it is not acceptable if anyone tells, okay, this is the modification, this is the update has to given. It is not acceptable in the way. Yearly there are like 3 different global meetings will be there. So first the draft test is submitted. So the draft review will happen. So the review is be done by the global community members. From the members from different globally institutions, organization, professors, and even industrial experts. So everyone will work on that document, the draft that you have submitted, and they will give you the review. So the review, you can think of the review questions would be like, why can't we like this? Why can't we do then this way? Why this has to be implemented? So many kind of reviews will come up. So once after that So the draft will be considered and the presentations will go on in each and every kind of meetings in the global meetings. So once after like a successfully implementation, once successfully accepted from the global community members, that standardization will be considered as an one of the networking standard, and it will be completely utilized from the industry bodies. So here, that's the where IETF is the there are under this IETF there are like an multiple working groups. Among that, these three protocol standardizations working groups also there. One is like an 6LoW. If you just look into the 6LoW working group in IETF, you will get that is the 6LoW PAN working group. So that is an IPv6 enabled low power device personal area network. And this role, yesterday you all have seen about an specifically the routing protocol, RPN, routing protocol for low power and lossy network. That is the one role. So that is the routing protocol working group role, and IPv6. So these three major things are into the IoT, that is with respect to the IoT network, 6LoWPAN network. So if we look into that, which are the industries are adopting it? So which are the industries are already working in this one? So many. If we see like an OGC is like an open geospatial consortium. It is an international voluntary consortium organization. So which is from the 1994. So that also accepted with the standards from the 6LoWPAN standards or also role standards and the IPv6 with respect to the IoT. And if we look into this ETSI, that is for an M2M. So ETSI is like an independent non-profit standardization organization. So that is in the field of like an information and communications, ETSI. And also this is ETSI supports to the development and testing of like an global technical standards for ICT enabled systems, and also for application and services perspective. And also ISA SP 100.11a, so that is also one of the standard body. This is a wireless networking technology. This is like a standard developed by the ISA, that is an Internet Society of Automation specifically. So this is where we can see even the 6LoWPAN adaptation is very good in the perspective of an automobiles as well. So 6LoWPAN adaptation not only in automobiles, we are going to look into this in industry as well, how it is growing as well. And IEEE 802.15.4 standard, ZigBee we know very well, and IP500 and IPSO Alliance is the one of the alliance body. So like this, different organizations, different bodies are accepting this specific 6LoWPAN stack, 6LoWPAN standardization, and working on this, and working on for the contribution to make it standardization. Okay, now I'm at the part of a comparison of a stack, 6LoWPAN stack. So we all know very well the 6LoWPAN stack that in this one, like I'm not sure how many of that. Before this is the 6LoWPAN stack. Before going to the 6LoWPAN stack, I would like to touch the very well known OSI layer. So that's like 7 layers of a stack. So yeah, physical layer, data link, network, transport, session, presentation, and application. So application layer, the protocols can be very well-known protocols could be like an MQTT. Most of you are already using it. I've used it specifically. And CoAP is one more the protocol for an constrained devices, constrained application protocol. Probably I hope yesterday in session you have used it, CoAP. So these are like different protocols are there. Just I'm naming few of them. MQTT is like a very widely used one. So in the normal TCP/IP protocols, if you compare the protocols like, and for example, in the RTP and HTTP based on the REST architecture, the application protocol, and the presentation layer and the session layer. In this one, I have explicitly mentioned that not used. Yes, in IoT stack, in 6LoWPAN stack as well. These two layers, like a presentation layer and session layers, are not used. So if I take off these 2 layers, I will going to remain with only the 5 layers. In the 7 layers of stack, so there are like 7 layers. In the 7 layers, if I'm not going to make use of these 2 layers, I will just return back with only the 5 layers. Very important. So why we are not going to make use of these 2 layers? It would be a very interesting question. So the first thing is like a session layer. In IoT devices, the session there will be no like a multiple session. If I consider in my laptop where the OSI like a TCP IP protocol stack is running. So in this one specifically, I have opened with an WebEx, I have opened with a Zoom, I have opened with a Teams, I have opened with different applications. So multiple sections will be there. The multiple sections will be handled by the session layer. I'm just going to give a high-level idea. And when we point to the presentation layer, how it will work, it is like regenerifies the data. So whatever the data I'm transmitting, so even if whatever the audio I'm telling and speaking here, and whatever the video just you are visualizing it here. So all the data will be like transmitting in the way after the physical layer. It will be like 10001, 10011. So it is completely like in binary bits. So completely binary bits. So must be someone to understand, oh, this is an audio, and he has to regenerify the data. So to an representationable format. So that is what a presentation layer is doing. So, but in case of an IoT, we don't want that as well. We are going to make use of only the digital data. If there is an analog data from the sensors, we are going to ADC conversion will be performed. The digital data will be directly transmitted. Super. So explicitly, that is going to be overload for our stack. So to make it lightweight, so we are not going to make use of these two layers. So, okay. So we have taken off the two layers and we made it lightweight because we are going to work with the constraint devices. This is very much important. So then I just returned back with the 5 layers. So I have like an application layer, transport layer, network layer, data link layer, and the physical layer. So physical layer, I'm just not going to touch it. For sure, the IEEE standards are there. So physical layer and data link layer. So even for a ZigBee, what we are using it is like an 888 802.15.4 standard. If it is like a Wi-Fi, I'm just going to make use of the physical device that is like an 802.11 standard. So that depends upon the communication. That depends upon the range. That depends upon the frequency that I'm using. It's not going to. I'm not going to touch that part specifically. So. You can specifically see here this MAC layer and this physical layer is completely an IEEE standards. We are not going to touch that one. And you can see here, so the remaining layer for us, and even I can make the IoT device to communicate. Probably most of you have worked on the Raspberry Pi, so the Raspberry Pi is completely on the. We can make it like a Wi-Fi as well. We can make use of an Ethernet cable as well. So 802.3 or 802.11. The 11 it can be like a 2.4 gigahertz or 5 gigahertz. It can be standard like an B, G, or it's with the 2.4, or it's like with 5 gigahertz as well, like an N and AC standards. So if in that case, we are just pointing to the IEEE standards, and that's when we're not going to touch. And the remaining layers are like an application layer and the transport layer and the network layer. Okay, there are 3 layers. Very interesting part. Only 3 layers are there. We are not going to touch the MAC layer and the physical layer, and we already dropped with the 2 existing layers, that is the presentation layer and the session layer. This is very much important to understand how the stack become very lightweight to make it fixed to the constraint device. That's right. In the application layer, so HTTP is there, globally in the network. So all the devices are communicating using an HTTP, like an API calls and all. So in that case, HTTP is completely making use of an architecture called as like a REST architecture, representational state transfer architecture. So in that REST architecture, if it is working on in our local network, so we must have a protocol that has to support to the REST architecture, because the proxy conversion will be very easier. So HTTP to the new protocol that we are going to use here is a QAP, Constrained Application Protocol. HTTP to QAP and the QAP to HTTP, these two are the proxy conversions. It is makes easy since both are making use of an REST, that is a representational state transfer architecture. And that's very interesting. The next one layer is like a transport layer. So in the transport layer, TCP, we know I'm very much interested about the battery usage. So battery is very much important. If I'm going to use like an IR battery especially for a TCP, if it is going to be like a 3-way handshaking process, I'm not interested in the handshaking and wasting my energy just like an hi, bye, and acknowledgement, which is unnecessary stuff. I don't want to use like a TCP. I would like to go with an UDP. ICMP, Internet Control Management Protocol, for sure we are going to use it in our stack, ICMP. And just to give one more information, TCP UDP probably very well know, we all like them very well know from many years. So there's one more interesting protocol called as a Quick protocol. I'm not sure how many of you are aware of it. Just have a look into the Quick protocol. The Quick protocol is also very interesting. You will get like a lot of open areas to do the research work and to work on to the protocol. Quick protocol, just got it in my mind. So have a look into the Quick protocol as well. It takes time consuming, so I'm not going in depth of it. And IP, there is a network layer. So network layer is the layer will tell you have to go in. This is the best path. This is the shortest path. You should choose this one. And this is like the IP network layer will choose based on, and also the IP address assignment and all. In the other specifically with an IPv6, the network layer will take care of it. So now coming to our 6LoWPAN protocol stack. So in this 6LoWPAN protocol stack, the interesting part, all the 7 layers you can see here. In these 7 layers, just take off the 2 layers that we are not making use of, a presentation layer and the session layer. So we already know why we are not using it. And the application protocols are there. So the QAP, Constraint Application Protocol, I already mentioned. It's very lightweight. The header is also like an around 8 bits, 8 bytes, I think, 8 bytes of an header size of the QAP compared to an HTTP. It's very lesser header size. And also, because I'm a 128 bits, if I'm going to give like for all the layer headers itself, that part we are going to see in the header compression part. That will be like a very interesting how we will make the header compression. So we want to reduce the space consumption as well. So and as well, in case of a transport layer, we are going to make use of an UDP and we are going to make use of an ICMP, and obviously we are our interest on the IPv6 instead of an IPv4. We want to support with a billion of devices. And there is one more new layer. Hey, we are not aware of this till now. That is like an adaptation layer. That is where 6LoWPAN, because we are adopting it. It was not there till now with us in our day-to-day life, where we are making use of an everyone, even from our mobile phone, we are making use of specifically the TCP/IP protocol stack. It is there, and even if I send some link request and if I send to any server, yeah, for sure, the voice layer is there. But now for that stack, we are going to adopt a new layer. That is what called as like an adaptation layer. The adaptation layer itself, the 6LoWPAN, and the 6LoWPAN, that is an IPv6 enabled low power personal area network, which is from the IETF, the body, working body, that's an Internet Engineering Task Force. Super. Well, we understood now the 6LoWPAN stack, which is consisting with an adaptation layer. It is completely like a 6-layer stack, but excluding that, our stack which is only with 5 layers. Super. But still, now I hope you all understood, because in this one, in addition, why I spent much more time here is this is very much important to understand, because TISH will come. This is like a standard. Okay, we made a fix. Okay, we have adopted 5 layers. We have in that one we adopted in between the MAC layer and the network layer. That is what an adaptation layer. Adaptation is there, super. But again, we are going to adopt one more thing in the next. First, let me tell the challenges and why we are going to adopt that. That is very much important. I will tell the TISH part. Why actually it is where we have to adopt it, where we have to place it properly. That is very much important. That part we are going to look into it. Before that, some questions will keep on rising. That is like is it possible to match IPv6 packet in 802.15.4 container? So that's some of the few basic questions all the time that we used to get is like yes, IPv6 is like a very huge packet, 1280 bytes, but 802.15.4 standard that you are talking about is like 124 bytes. Are you going to support that? How could you support? Because there's a huge amount of data will come up to your network, right? It's like a very the information is just coming in a lorry. I want to transmit in some small nano car in the way. So how can it be possible? In that case, yes, we can make it in our 6-LoWPAN stack, it will support with an three operations, that is with an fragmentation and reassembly, and the second thing is like an header compression. These two, the three major process will be done is like an header compression, fragmentation, and reassembly. These three are very much important. That will be taken care of in the 6-LoWPAN stack. Fragmentation, actually what it is means, you can say here, if IPv6 packet with 1280 bytes with an MTU size, if the information is very lesser than around 127 bytes, it's very good to go. There will be if it is very good to go with 127 bytes, that the information is completely passed in the not a fragmented one. If it is very huge packet, then the packet will be fragmented. So there will be a very first packet will be consisting in a fragmentation header. The fragmentation header will be consisting in information related to the number of fragments, how many fragments are generated, and what is the unique ID. Fragmentation ID will be there, and specifically the fragment identification bits will be there. I think there's 3 bits of an identification, and followed by the fragmented packets. So that will be consisting with mesh addressing header. So the fragmentation and reassembly will be possible. So if it is 1280 bytes, so it is going to make it fragment in 10 packets, and the same fragmented packets will be reassembled in the receiver side. So that will take care in the low-PAN network. So that's very interesting. Yeah, that's what that's what, as I mentioned, if the maximum packet size is with respect to 1280 bytes, and since our 6-LoWPAN stack, 6-LoWPAN network standard MTU size is 127 bytes. So if it is in Premier, as I mentioned, the very first packet, so that will be consisting the number of bits specifically 16 plus 11 plus 5. So 32 in this one, the first 5 bits will represent, that is the Premier fragmentation packet, that is 11000, and followed by fragment subvariant, that is the packet which is followed by the first one. So that is 11100. So this will be a standard to identify this is the packet, okay, the information. And that will be followed by the datagram size and the datagram tag. Tag will be keep on increasing for every new packets, and the datagram offset value. Offset value for every unique packet, there will be how many number of packets will be there. Those number of packets identification will be given with an unique, which will be helpful for the reassembly process. And next one. So problem is optimizing the transmission of IPv6 packets over low power and lossy network. So this is one more very interesting question. So we have 127 bytes of a space, 127 bytes. In that 127 bytes, if I'm going to give the 40 bytes, because IPv6 header size is 40 bytes. If I'm going to give the 40 bytes directly straight away to the IPv6 header, I'm going to return back with around 87 bytes itself. Because in 127, I'm just going to step back with 87 bytes. In that 87 bytes, again, my application protocol will take some header space, and my transport layer will take some header space, and also my MAC layer space will take up some header space. And so if I keep on giving just for instead of my payload, instead of my required actual data, if I give all the space to the header itself, I'm just going to return back with a very, very less amount of space for my payload. So if the less amount of the space for the payload, then the challenge is I can create multiple packets, but the traffic is going to increase in the network. As the traffic is increased, we are well known packet collisions will happen, and the packet loss and retransmissions will increase. So, and power consumption will increase. That is a very bad idea. So to overcome all these problems, there is a solution called as an header compression. So header compression, I will just go through this header compression part. So 6-LoWPAN header compression, how it will happen, I will just walk through it. 6-LoWPAN maximum transmission unit, as ZigBee, it is 127 bytes. Yes, very well known. And it is in 127 bytes. Cool. In that 127 byte, UDP header will be there in the transport layer. So the UDP is also going to consume some 8 bytes. Yeah. Okay. I'm like a very give person. Okay, just please take another 8 bytes of space from my 127 bytes. I'm giving UDP 8 bytes for my UDP header. After the very transport layer, there's a network layer. Oh, I need IP, the two IPv6 header. IPv6 header will ask 40 bytes. That's very huge. In that 127 bytes, IPv6 header is asking 40 bytes, which is a huge space, right? So if I'm going to give the 40 bytes, so totally in 127 bytes, I already gave away 48 bytes. So after anyhow, the packet again, when it moves to the next layer, that is our MAC layer. So again, the MAC header will request for 25 bytes. MAC. So this is really, I'm not going to have any space to transmit my data. That is with a payload. So whatever the space that I have, it is getting filled with specifically with the headers. So that is with an UDP8, IPv6 40, MAC with 25, and in total it is like 54 bytes. So that I have for an payload. Very bad. So even not an half of the MTU size. So only 54 bytes, even I'm not considering the QAP header as well. So just without considering the application protocol header, so I'm just going to return back with only like specifically 54 bytes. If I look into it seriously, who is going to consume more space? Where I can make it lightweight, where I can get more space. So who is the guy which is occupying my all the space? So at that time, we can easily point to an IPv6 header. The IPv6 header is the guy who is consuming 40 bytes. So I have to make it like very lightweight. So then I will point out to the IPv6 header. I want to compress that. So that's where I want to compress the IPv6 header, specifically, which is 40 bytes. I want to compress as much as possible. So when I compress it, I will get more space where I can place my data, my payload information as much as possible. So yeah, this is like an just as I'm getting in mind. So as like when the number of fragmentation has increases, the traffic will increase in if it is from any of the metro city, we can see nowadays the traffic is a bit less due to the COVID. Thankful to COVID for reducing the pollution. Okay. Now, okay, we are very much interested in reducing the IPv6 header. Now we have to understand how can we reduce the IPv6 header size? How can I increase my payload? Just think of it. Obviously, for IPv6 header is 40 bytes. Okay, I'm only working 54 bytes. So the next, let us see. You can see here, just we are like completely opening up the IPv6 header. So the IPv6 header is completely within 40 bytes. In that 40 bytes, if we look into it, when we deep dive and look into it, so there is so many sections, header fields like an version, traffic class, flow label, payload length, next header, off limit, source address, destination address, and the header compression 2. That is the next header compression 2 encoding part. Okay. Okay. The cool thing is now, how can now I want to verify each and every field. Do I need this or don't want? So that's what we are going to do now. So the first column tells these are the header fields, and the second column will test this is the IPv6 header length, means what actually the IPv6 header is using, and the third column will tell what actually we are compressing and what actually we are utilizing and what actually we are not using it. So version 4 bits. Do you really think like do we need to make use of 4 bits specifically? 4 bits is very expensive for me. Yeah, 4 bits specifically just to represent it as an IPv6 network. We know very well we are making use of an 6LoWPAN. It is completely an IPv6 based. And do we need to know the receiving device? So this is an IPv6 one? No, for sure, no. So that's the reason completely I'm just completely going to take off these 4 bits and going to assign only the 0 bits for the version mentioned. So I'm going to save 4 bits. The same way, following like in traffic class is like an 8 bits. No, not at all. Just to mention the traffic loss on 8-bit, I'm just going to like in 2 bits are good enough, like in 0 or 1. So 1 bit is assigned for that. Flow label 20 bits, flow label for sure not at all, and also like in payload length. Okay, payload length you may think of 16 bits, it is required, but in the same payload length, information will be kept in the MAC header as well. In the MAC header as well, the payload information will be there. So we can get the device, receiving device can get to know about the payload length in the MAC header as well. So there's no requirement of keeping the payload length twice in a single packet. So why to repeat the same information twice? So that's the reason we are going to completely take off the payload length as well. So then we are going to save 16 bits here. Next header. So in 6-low-pan stack, the next header completely we can mention it like it can be like in 4 kinds of an headers. So 00, 10, 11, or yeah, 00, 01, 10, 11. So like in 4 different kinds of an header can be represented. So in the next header will be kept. Only the best uncompressed part here is, you can see here, the op limit, which is very important. Yesterday you all seen the routing protocol RPL. So just if you have observed clearly, it is completely an acyclic graph. It is completely an acyclic. It is not like an. Have you seen in the network in the graph where they have demonstrated? Have you seen any of the cyclic formation there? Not at all. The completely RPL is an acyclic graph. It is in a tree structure. So even when the child nodes connect to the parent node, it will keep on growing as in the formation of a tree structure. So acyclic graph. Since it is like an acyclic graph, by any chance, by any like an bug, if the packet just return back, it's just stay back in the loop information. So it is just keep on hopping in a network, and once it reaches the maximum, like into the like an 8 bits, that to the power of an 8 number of hops, then that packet will be like taken off from the network. So this is the op limit, which is very much important in case of an say a network. So that's the reason that complete 8 bits we are going to return back as it is. Source address and destination address. Yeah, 128 bits for source address and destination address as well. 128 bits. But how can be? It can like 2 bits. You can see here, I think. Can I make use of 2 bits to represent the 128 bits of an IP address? So that's like a very interesting. Oh, yeah, 2 bits specifically. Why we are using here? Because if I keep only 2 devices, one-to-one communication, I won't call it as like a network. At least I need like more than 3 and more. So 4 devices I need to create one network. So in that case, multiple device means at least 4 devices I'm considering. So in that case, the very least network. So very least number of device in a network, that with respect to the 4 devices. So I'm considering the 2 bits, 00, 10, 01, and 11. So totally with those representation, I can place 4 devices in a network. So by placing 4 devices in a network, I can make them to communicate each other. And so that's even when the number of devices are increased, so it can be like a 3 bits, 4 bits, 5 bits. But as much as we are compressed, so we can compress it till the 2 bits specifically. We can't compress it like more than 2. If it is only within 1 bit, then it is only like a 0 and 0, 0 and 1, like specifically, and 0 and 1. So that is with only 2 devices can communicate. So that's like a one-to-one communication. So to make it like an as much as possible, we can compress that. We can compress it till like in 2 bits, both the source address and the destination address. And the next header, that is like a next header compression to identify encoding that, which is not there in the IPv6 header, but we need it in 6-low-pan. That we are going to represent with respect to the 1 bit. It can be like a 0, 0 or a second 0. Sorry, 1 or 0. So either this next header is compressed or not to represent it. So once after all this compression, once after all this jagged, like and what we will do, okay, we what all the stuff we don't want and what all the unwanted stuff, just like in cleaning process. Once we make the complete cleaning process, we have saved like totally 38 bytes. The total IPv6 header length is 40 bytes, And in the 6LoWPAN header compression, so after the complete compression of the 6LoWPAN header, we have saved like in 38 bytes, and we are only want like in 2 bytes. Just I want to go with an previous slide. You can see here, IPv6 was making use of an like in 40 bytes, and it is like for payload it is only like in 54. So I have saved like an nearly like an 38 bytes. So 54 plus 38, I can make it like an I can getting like an additional huge space to place my payload. That is for my information. So that is actually a very interesting part. So this is the complete header compression. I tried my best. So if you have any queries, we can take it up later. So this is the complete header compression which happens. So we have seen the major 3 processes that is done by 6LoWPAN, that is like an header compression, fragmentation, and reassembly. Hope you all. Oh, okay. There's the next one more question. Device address management require a lot of message, stateless auto configuration. That's with like an neighbor discovery process. How in the IPv6 will happen? Stateless auto configuration, that is like with respect to the stateless IPv6 neighbor discovery process, that is like an requesting the solicitation and the acknowledgement and announcing. So that kind of process will be same kind of a process will be followed in case of an 6LoWPAN neighbor discovery as well. And for this, we will make use of like an with respect to the protocol that's yesterday. I hope you all seen that an RPL routing protocol for low power and lossy network. It works completely in the distance vector routing protocol. So it mainly target like a collection based network where nodes periodically send measurements to the collection point, and it contains like thousands of node devices in the network. So just I want deep dive into that part, routing part, since you are already you all know very well about that. I'm just skipping the RPS stuff. Oh, okay. With respect to the security, so what are the security aspects in 6LoWPAN? Yeah, a lot of like an ad security mechanism in there on the network layer and the application layer. So in the application layer, like a DTLS datagram transport layer security will be there, and the UDP and the IPv6, which is supporting with an IPsec, and the 6LoWPAN is also supporting with an lower send is the security, and AES encryption in the MAC layer. That is a 15.4 AES encryption. You all know very well about that. And okay, this part I already explained this one. HTTP, which is on the REST architecture, that's a representational state transfer architecture, and even on today answer section, we are going to make use of the QAP. So constrained application protocol. So why we have chosen how the QAP is designed means it is very way in the similar way how the HTTP is designed. The HTTP completely works on REST, and the QAP will also completely work on the REST architecture, the representational state transfer architecture. So since these two are completely designed in the same architecture, you can see here, QAP to HTTP, HTTP to QAP, the proxy conversion is very easy. So the gateway, the proxy here, it is a gateway device. So it makes the work we made it easy for this gateway device. It will easily convert the data. What this is completely constrained environment is completely the local network. Probably all created in a 6LoWPAN network in yesterday in a Kuja simulation. So whatever the network you have created, that is like an ad hoc network. So once we placed a gateway, it's like a completely a 6LoWPAN network. So in that 6LoWPAN network, so there's so many devices will be there. All the devices will communicate, and it is like completely an RPL routing structure based one. And those devices will be communicated by making use of a constrained application protocol. But in the global, if I want to store the data, which is, for example, if I want to store the data in the blob storage in Azure, even in case of an AWS or any of the cloud, or even in my own server. So in that case, I'm making use of an HTTP. So it's very much important to know. So how to perform, how to make the conversion for the gateway is the responsibility of the gateway. Oh, this is a QAP. He's telling him from the QAP language. I have to inform to that guy, to that server in the language of HTTP. That conversion, that proxy conversion is very much simpler, made it simpler in this one because of the REST architecture, since both are saying. The proxy conversion is very easy. Okay, 6LoWPAN MAC layer. Um, so I'm just touching the each layers, and then I will point to I will jump onto the specifically the 6 stage. I just want to give an overview, like a clear understanding of the stack. So then it makes easy to pitch into the ground, to play very well on the ground. That is on our hands-on session. So without like a clear understanding, okay, just drag and drop, kind of it won't looks like. So this is completely, if you know the understanding very well, we can play very well as well. The rules, we can tell it like an, if I'm going in a, going on a road, so there's traffic signals and some rules are there. In the same way, these are the rules to transmit our packet in a network. Okay, MAC layer. In the MAC layer, there are 4 different kinds of there, like an that we are going to see. The first one is like a null. So whatever the 6LoWPAN you will design, the application or as the specifically whatever the standard or whatever the use case specifically you will design. So it completely, the designing architecture completely depends upon your requirement. For example, if I'm going to design a device which is always connected to an power, so I'm not concerned about, I'm not bothering about a power. In that case, it is very good to make use of a null MAC, because it clearly, here I'm just clearly stating that it simply forwards the packet in between the network layer and the radio driver, and no power saving at all. This point is very much important. No power saving, so it won't bother about the power saving. Means this device is assuming that the receiver is always awake. The receiver is always awake to receive the packet. So that means the receiving device is not going to the sleep mode. So in that case, the power consumption is very high. So means the power saving, no power saving at all. It is like a zero power saving. Oh, so in that case, nullMAC is good, but the device, the use case, what we are developing, it has to be like connected to a source of power all the time. So the next one is like an XMAC. I'm not sure either I have a diagram. Oh, okay. Okay, next one is like an XMAC. In the next XMAC, how it is means sender uses sequence of short preambles like a strobes to wake up receivers. For example, I'm just like an we both are considered. We are you are also like a sensor device. So many sensor devices are there, and I'm also like a transmitter. One of the transmitter. I want to transmit some information to you. At that time, it's in the way I directly won't transmit the actual information. I want to send something specifically, some time slot I want to send, or some information I need to give. I won't give that information directly. I will just tell like in short strobes. Strobes is like in hey, hi, hi, hi. Some kind of an repeated strobes that will be transmitted. So these strobes just to make the receiver wake up. So once the receiver wake up, because the receiver is always very concerned about its power, it will be in a sleep mode. Once the receiver wake up, it will give me the acknowledgement back, hey, I am awake. Oh, okay, then I'm like, oh, okay, you are good. Then take this information. So this is the way XMAC will work. And after the information, the acknowledgement will be taken. There's one more thing that is called the low power probing. That's an LPP MAC. That's a low power probing. So here, receiver periodically send. In this case, I'm the guy who actually supposed to transmit the data, but I'm quiet. So I'm not sure at what time as a receiver you will be awake or is in a sleep mode. Not sure. So as a receiver, you will wake up and you will ask like you will send this some kind of a probes to me as like an I'm just awake. Do you have anything to transmit to me? Do you have any information to transmit to me? So just you will keep on sending the probes whenever you are awake. So when I receive the probes, okay, hey, I will tell that, hey, yeah, I have some information to transmit to you, and I will send the actual information packet. So that is where we're looking low power probing. One more, the combination of these two is the quantity MAC. So in the quantity MAC, a receiver periodically sends small packets called as probes to announce that they are ready to receive the packet. Let's see in the diagram itself. So this is the XMAC. In the XMAC, so what we have discussed here, there we are sending a strobes, right? So this is like, so this is the topper one is the XMAC, and the below one is the quantity MAC. Just try to understand. So in the top one, let's look into the topper part, the other than upper part. So that which is an XMAC. So the upper part XMAC, there are two devices are there. One is specifically an transmitter, and the another one is like an receiver, specifically. So what we have read. So sender uses a sequence of short preambles to wake up the receiver. So the guy who is like a transmitter, he will keep on sending some packets like strobes. So this is what the receiver is slept. The radio is off. Is very much concerned about specifically to save the power. So is completely off and is not listening at all. At that time, the transmitter has some very much important information. You will keep on sending the strobes. Okay, so keep on sending the strobes. So whenever the receiver wake up, you will give back an acknowledgement, and this is the data. Data will be transmitted. In case of Conti-KMAC, the same thing repeat here after this as well. After transmitting the data, the same thing is represented here. In case of Conti-KMAC, just I will try to understand the Conti-KMAC. In case of Conti-KMAC, you can see here this D that is with an dark red, which represents the data. So the D is a data which is keep on transmitted here. What the mean is, instead of sending the probes multiple times, probes, so why can't we transmit the data itself directly? So the Conti-KMAC what it will do, what it actually is doing is like and completely keep on transmitting the transmitter as a transmitter, keep on transmitting the data. Whenever the receiver receives the data, hey, I received the data, I'm successfully. That's what an acknowledgement it will give, and it is done. So this is the Conti-KMAC completely based upon the power saving mechanism. We can make use of the MAC layers and we can work on it. Okay, till now. So this is completely like an 1 hour duration. In 1 hour duration, just we have seen specifically like an the 6LoWPAN stack, and we have seen the 6LoWPAN stack. We have seen the completely the cameras. RPL only the part we are not touched, and the remaining like with respect to the HTTP, fragmentation, reassembly, header compression, and few things we are just seen, and also the MAC layer we have seen. So next, I hope now you all understood about an 6LoWPAN stack. It's very super good one. So now it is the time to understand the TISH part. I just wanted to make you all understand the complete the 6LoWPAN layer. Just now I'm entering into the TISH part. Yeah, hands-on. Don't worry. We are going to play with an hands-on. It's not mean that I'm going to consume much of the time in the TLD part because hands-on is not much heavy. Just I will take like 2 minutes of break, not much more than that. 2 minutes of break, and we'll start with the 6-TISH part. Okay. Okay, we can start back with the 6-ish part. So I hope everyone understood the 6-low-pan part very well. So it's time to like, and we can see the like a 6-ish. Till now, we are seeing like in part like in 6-low-pan. What is this TISH? That is like a new standardization effort to combine IPv6 connected to an industrial IoT. So it's like an yeah. Why actually do we need it? Because we are from like an making use of an IoT that is specifically the M2M machine to machine from long back, and we are with a Zigbee IP, 6-low-pan, as I mentioned, like an Z-Wave or as like an Wi-Fi with respect to the Wi-Fi also even a BLE as well as an BT. A lot of stuff is there. What is the new standardization that is an ITF? You all may like with respect to the ITF. This is also with respect to the ITF. So what is the new standardization? Why actually it is? So let's we'll try to understand this 6-ish actually. What are all the challenges were there, and we'll try to understand the technical overview of the 6-ish specifically, and what actually exactly it is going to define what actually exactly the problems it is going to solve. So that's what we have to understand very much important here. Okay. My slides. Okay. So first part is like an wireless challenges. We know very well. There is like, and we know very well like in the part is like with respect to 6-ish. Okay, the thing is like IoT we know, and what we know if we can able to communicate in between the devices. What is the wireless challenges we have? There are so many different kind of challenges out there. So we need to understand even after the like a 6-low-pan or like a different kind of an emerging technologies that we are using with respect to the IoT. So what actually the challenges are faced here? Let's look into the first challenge, that is an external interference. This is the one. So in this external interference, okay, once of the slides are just, I'll just modify the slides in using a web. After downloading it, it is showing in a due to the format I'll just modified. Sorry for that. So you can see here, this is completely an frequency spectrum in this one. So our Wi-Fi devices that like respect to like an 802.11 or as like in Bluetooth, which is Wi-Fi, which is represented in the red circle, and also like in Bluetooth 802.15.1, so which is the bluer one, and as like in 15.4. So that is like in 2.4 gigahertz if we consider with respect to the frequency. So devices can communicate in the same frequency, even Wi-Fi. My Wi-Fi device is also working with the same frequency, and Bluetooth is also working in the same frequency, and also my IoT device is also working on the same frequency. There's a lot of possibility for the packets to get collided. And once the packet has like and due to the same frequency and if it is like a same channel number, so at that time, so the lot of collision possibility. If it is the case of like an you can see if it is a case of like in channel number 18 or else like in case of a channel number 22, the packet collision rate will be very high. So even if my Bluetooth device is also making use of the same channel number, so Wi-Fi, Bluetooth, and as well as the specifically the IoT devices, all the devices are communicating in the same channel number, and the range of a packet collision and the probability of a packet collision will be very high, and packet loss will be high. As the packet loss increases, the retransmission process will be increases. So this due to this is one of the major challenge actually in IoT, and we are not done with this challenge. We have another challenge. So even if we don't have any of these specifically other devices, multiple devices, so we are facing another challenge that is called as like a multipath fading. So multipath fading means so there is a device A as a transmitter and the B as a receiver. So the two devices are just separated within a few distance. And whenever the data is transmitted, the data is not transmitted only in one direction, right? That is not in like in direct way, that is like in PD. It is not transmitted in one direction. The data will be transmitted in all the 360 degrees. So whenever the data is transmitted, there is the chances of whatever the data transmitted to an in the other direction, it can collide to some of the particle and it can reflect back. Whenever they reflect back, the information which is transmitting in the one direction and the information which is got reflected, it will be in the same frequency and the packet collision probability will be very high. So that we'll call like a multipath fading. So to understand this multipath fading process and to understand this specifically the challenge, so one of the experimenters done from the TISH working group. So what they have done is, so they took up like an two devices. One is like a transmitter and the another one is like a receiver. So this transmitter and the receiver is just separated from an 100 centimeter, not far away. You can try once with if you have an embedded device or if you have like a two IoT device, just try this try this experiment. This sender and this receiver is just separated by like an 100 centimeter. So as we can see here, this is like a sheet of paper. In this that like an 20 centimeter cross 30 centimeter 35 centimeter area. In this area, the transmitter will be keep on sending the like a burst of packets, like and it will keep on sending like 1,000 of packets. What's my expectation as a guy, as a layman? Oh, this is the transmitter, this is the receiver. Okay, my packet has to information has to transmit very fast away. And my expectation, what is it in generally we will think of? We will think of all the packets, all the 1,000 packets must and should be received. This is what our expectation, right? Just to think of. Very closely in the 100 centimeters is not too far away. The receiver is there and transmitter is there, but the range of the devices will be very high in the meters, like 100 meters. So in that case, I'm expecting if I send 1,000 packets, the receiver must receive the 1,000 packets. If I send 1,000 plus one packet, the receiver must receive the 1,000 plus one packet. That's what expectation. But in general, in normal scenario, so the count varies. Count varies a lot. In between from the centimeters difference, also the count varies a lot. So that's what the research team has worked on the specific challenge. So they, as I mentioned, they took up the two devices, one as like a transmitter and the receiver, and by placing the device all over like in 20 plus 35 centimeter area sheet of paper by moving the device with specific frequency. First, what they will do, they set a frequency. So you can see here, they will set a frequency that called like a channel number 11. So in the channel 11, there's like a first 2.4 gigahertz frequency in that channel number 11. In the first channel number 11, so they are going to just burst the packet like 1,000 packets. And the receiver, what they are making it is just they are moving around the sheet of paper, and when they are moving around just like in between around it like in 20 cross 35 centimeter area, they observed a lot of change. So you can see here wherever there is a dark red part, so it represents completely zero packet reception. So the number of even the device are very close, the number of packets received is very less. So whenever the packet is like a bit far away, so whenever one greener one, you can see here the number of packets received is like 1,000 packets, the 1,000 packets are completely successfully received. But we can see here the complete dark greener is very less, the part is very less. So the same the same specific experiment with the different channel numbers. So you can see in this diagram, so the different experiments which is done with respect to is like in channel number 11, channel number 12, channel number 19, like in 13, 14, 15, 16. So in the same way, the experiment has done till to the channel number like in 25. So you can observe here, same devices, same location. So if the channel number differs, the probability, the range, or I mean the probability of receiving the packet will be very high. If it is in the case of channel number 11, you can see here it is like a lighter greenish, means the probability is very less. It is like an probability is like an half of the percentage. But in case of channel number 12, the percentage of packet reception is like completely dark green. We can see here the packet reception range is like a very high, and the percentage can be like a 98 to 99% of packet will be received here. So that's where it is like in dark green, it is mentioned. So the same experiment is done with the different channel numbers, channel number 11, 12, 13, 14, 15, and now they understood that. So if there is any channel, if there is any challenge with respect to in between the two devices, and they are transmitting the packet, so whenever there is a change in a channel number, the chances with respect to receiving the packet will be very high. So that's the way Tish came up into the picture. So, okay, there are two challenges. There are two wireless challenges out there. So they took up like in challenges like in multipath fading and all. So to overcome these challenges, they tried with this experiment. So one is like an external interference and the another like in multipath fading. So they understood, okay, these are the two challenges, and they tried this experiment. So once they tried with the experiment, so this is the solution they have to come up. So for that is the reason they bought into a new solution, new standard, that's okay, IEEE 802.15.4E. Let me change my slides. Just give me a minute. I'm just trying to change my slide. Yeah. Okay. So now this is the actual the 60 stack. So in this stack, whenever you look into this stack, someone is speaking. Please mute yourself. Okay, cool. Yeah, they're muted. Thank you. I can see them. Okay, they're muted. So let's come to the point. Just I'm switching between the slides. I'm sorry, the content is in a different slides. That's the reason. So yeah, this slide is bit looks good. I hope you are able to see my screen. Yeah, sharing is working fine. So second challenge is like in multipath fading and external interference. The two challenges are there, and the experiment is done in between the different channel numbers, and we have observed. Oh man, even in like an 100 centimeters difference in the 20 plus to 35 centimeter, and the packet reception is like a very huge difference in them. So specifically, the packet reception in the perspective of whatever it is transmitted from the transmitter. So to overcome this challenge, to overcome this issue, so that's the way 60 came up with a standard called as like an IEEE 802.15.4E. So we know very well till now about an IEEE 802.15.4. So this is like a new standard. That is what an IEEE 802.15.4E, that is written 60. Okay, this is I'm showing as like an Internet of Things stack. So Internet of Things stack, you all like what you have seen till now, it looks similar way, but some difference. So let me just give you an idea about this stack. QAP, we have very well discussed about in QAP, Constant Application Protocol, application layer, will not worry about that one. Integration part, internet integration part, yeah, the network and the transport layer, that's the UDP transport layer, will not worry about that. Presentation and session, we are not touching it. And the network layer, yeah, IPv6, in addition to that, there is an adopted, just now what we have discussed, adopted layer, that is a 6LoWPAN, we are not bothering. And just scheduling, There is one part which is required specifically to schedule the hopping, should schedule the channels specifically for the reception of data. So whenever there is an observation of a packet loss is increasing, the completely devices has to be scheduled to one channel number to the another. This is what a gap we have found. So what the gap we have found here. So that is the gap. We call it as like a scheduling gap. So that is where 6-dish group is working on. So that is in amendment with the MAC layer. That is not in amendment with the network layer. So this gap in perspective in amendment with the MAC layer. So that is with respect to called like standard as like an IEEE 802.15.4E standard. So this is where the standardization, 6-dish standardization came into the picture. Okay, some of the information I have about the status. I think this is a bit very old status. The first standardization was published that is with respect to the published in April 16th, 2012, which is a very older one. So you can refer into that document just for reference. I am keeping up. Coming to the communication schedule. So communication schedule is very much an interesting part. I have another diagram. Yes, slot. Okay. Coming to the communication schedule part. So here you can see there are 16 channel offsets are there. And this is the network. So where A is like a gateway device and B, C, and all the D, E, F, G, H, the completely like an device are connected on each other. And there will be an it's like a super frame. There will like an repeats completely for every certain duration of time. There will be one of the frame for a packet transmission will be keep on repeating that we will call like an specifically super frame. We will call it as. This dish is like a basic to complete like a link layer protocol. So it is what the working group is telling. It is like in distributed scheduling protocol specifically. Okay, number of slots in the super frame is tunable. So let me explain this part. So there are like 16 channel offsets are there. There's one super frame will be there. In the single super frame, there are like different channel offsets will be there. That will be specifically like 16 channel offsets. So each 16 channel offsets, the slots will be keep on giving to all the devices. Whenever any device observes there is a packet loss, whenever there is any observation with respect to the reduction in the packet loss due to the collision, due to the interference, the device will switch to the other channel. These are the 16 channel offsets means which is with respect to the like 11 to 26, the channel numbers. That's like with respect to the 2.4 gigahertz. So for every year it had took like 310 milliseconds. For in that duration of time, this is that what we will call like a super frame. In that super frame duration, so the frequency what it is chosen to transmit from the device E to the C is like a specifically pointed here. So if we point it out, it will come like an 12, 34, 16 channel number 16 something as an example. So then it will packet in the specific channel number, and that information will be broadcasted to all the devices, and all the devices will switch on to the new channel number, and it will receive the packet. So this is what the complete single slot. Each slot will be considered like a single slot. In the single slot, what all the stuff will happen? So the first slot, the total slot duration is like 9.976 milliseconds. It is not in seconds. It has to happen in a very faster way. And the first, just we consider like a single slot. In the single slot, 2.120 millisecond is to like preparing to receive in what actually the data has to be received. The device needs some time to turn on the radio and to just to prepare for that one. So the transmitter is getting ready to transmit the packet. Meanwhile, this is the receiver. Receiver is just preparing to receive the information. So with respect to the TSRF offset time, we will call. And then this is where the information is, which is greater than or equal to 4256 milliseconds, the transmitting the packet. So here the receiver has to receive the packet in the meantime, and then once after the reception is done, there is a specific acknowledgement will be there. So if any NAC has to be transmitted, that has to be informed in the duration in between like a 0.800 milliseconds or 0.400 millisecond duration. That will call like a time slot 3 and time slot 4. So did I mention? Yeah, you can see here like in T2, T3, and T4. So these are the different like slots. And the complete time slot in a single slot, so in a 9.976 millisecond of a slot, so the complete transmission and reception of the packet has to be completed in a specific frequency. Okay, this is how it is like in channel offset will be calculated. So as I mentioned, these are all the channel numbers, and channel offset is like considered as like an 11, and the channel slot offset is considered as like an 14. So in the frequency, which frequency channel number means channel offset plus ASN and percentage of an like a 16 plus 11. This is the we will be calculated. This is the formula. Just I'm not getting deep dive into it. I'm just moving into the part of hands-on. Okay. I hope you all got an idea with respect to the 6-dish. 6-dish is just to synchronize, as the name itself mentions. So it is a time synchronization based. It is like an completely 6-dish, as the name itself specifying. On specific time basis, the channel numbers will be keep on changing. So all the devices will switch on to the new channel number, and all the devices will communicate in a specific channel number to make sure that there will be no interference and there will be no packet loss will be there. Okay, so now switching to the hands-on part, I will just switch on to my Linux device. Those who are making use of an instant quantity, just feel free to turn up your virtual VMware. And once in a VMware, just start with your instant quantity. And in the instant quantity, the password is user, the default one. So as you all yesterday used it, using the password, the same password. Just make use of the password as a user and just get ready for the hands-on session. Meanwhile, I will just switch on from my Linux device. So there's no difference in between the instant quantity and the normal, just like a Linux, Ubuntu, or any other platform quantity 2.7. Instant quantity is just like a virtual your Linux itself. That having an ready quantity operating system and ready tools. It may be emitters, or it may be a Python, it may be an compiler, the required compiler, it may be an other packages, the required packages. All the existing packages will be deployed in that instant quantity. Okay, I will share my screen from the Linux device. Just everyone open up your virtual VMware and instant quantity. Just give me 2 minutes. Meanwhile, everyone just turn on your virtual machine VMware and turn on your instant quantity. We are going to make use of an instant quantity now. And yeah, I'm good to share my screen. So yeah. It's you may all think of it like an instant quantity will support with an OpenWSN. OpenWSN, another operating system. So there are so many operating systems out there, even previous like TinyOS, ContiOS, OpenWSN, and so many different out there. So today, what we are making use of is like a completely an OpenWSN operating system. I hope everyone have followed the steps which has shared to that is like a mandatory, the initial required steps to install the required packages for the OpenWSN, that is with respect to the 6-dish simulation. 6-dish simulation is just like looks somehow different visualization with respect to the if you compare with an Contiki. Okay, I will just share my screen. Just give me 2 minutes. It's taking time to load. Um, okay, cool. I'm able to share my screen from my Linux device. But this is okay, cool. I hope you are able to see my screen. That's what Control L. So those who are good with Linux, I hope you are able to see my terminal as well. So instant Contiki, in that one, I'm not sure where you all just cloned it. There, wherever it is, you must be able to see an folder called OpenWSN. Just search for an folder called OpenWSN ls. So it could be in your home file folder. You must be able to see an folder called as like an OpenWSN. OpenWSN is an operating system. I hope everyone have this folder. Those who don't have the folder, that's like an OpenWSN, just I will share the commands. You need to follow all these commands to make sure that to clone the required repository, to clone the required specific operating system, that is an OpenWSN operating system. So those who have an OpenWSN, it's good. I'm just repeating the steps. I'm just clear. So open your terminal. The terminal you can open by, there is an option in the instant quantity, just click on it, the terminal. So when you click on the terminal icon, you will get a black screen like this. In the black screen, just give ls to list out all the folders. So if you are able to see the OpenWSN, it will be in your home directory. In the home directory, if you are able to see the OpenWSN, that's good. In my case, it is inside the downloads. Inside the downloads, if I give ls, I can see an OpenWSN. Just I'm giving a time for everyone to make sure that you will figure out the OpenWSN. Just make it. Once you are able to get this one, just cd change directory open WSN and ls. So these three folders must and should you have. So the three folders are like an cohab, open visualizer, open WSN, firmware. So make sure that you have these three important folders, which is required for your today's session. Those who don't have, those who have not followed the steps, I'm just sharing in the chat box the commands that need to be executed. Chat box, yeah. I'm not sure whether it went to everyone or not. The host, please check that one. I just shared in a chat box. I'm not sure whether it's sent to everyone or not. To BIT Bangalore, I have shared it. Okay, so in a chat box, or else even in your WhatsApp, probably the ma'am have already shared the comments. So those all the comments in you must and should have to execute and to make sure that all the commands that you have executed, and this is very much important to have these folders. I will explain what actually these folders are, and coap, probably when you look into it, you will see this coap is looks like familiar. So this OpenWSN, in this one, the first part, that is like an OpenWSN FW. Just give me a minute. My Linux machine is just giving me an trouble. It's on. So today it is completely like to compile and to run the OpenWSN like in the simulation mode and to ping the devices, IoT devices. My Linux device is just rebooting. I will take 2 minutes. I'm sorry for that. So you can make use of in Windows as well. So those who are this OpenWSN can be executed from the Windows as well, and even from the Linux as well. The support for both as well, and it can just to create and simulated devices and to interact with over the QAP, that is a constraint application protocol. So to support with respect to the embedded devices, this specific OpenWSN, even it will support for an multiple various embedded devices similar to an Quantica operating system. It can be like an MS430, or as it can be either from the Texas instrument, or it can be from the STM32, or as it can be from the microchip, or even there is a specific from the OpenWSN itself. There is a specific board called it as like an open mode. So the mode it is called as like an open mode. So that can also be utilized.
Sir, I was able to do the third one, that is get install -y git, but the directory I'm not able to find.
GID. Oh, CD open WSN. So that directory, it has to be generated. There is a command called as like an make directory. Okay, anyhow, those who are facing challenge, I will just execute the command and I will show in my system once.
So yeah. 1 minute, I have just shared my screen.
Yeah, please.
So it's come here till here, I've got it.
Okay, CD open WSN.
So I was able to, because I didn't have open WSN. So I did the first one, sudo apt update. Yeah, then user password I gave and extracted it. And then make directory open WSN. Yeah. That I got it. And then when I tried the CD going back and then open the WSN, it's not giving. So should I list it and then find out? Where the
OpenWSN is there. See, I think there is a one mistake. So after the CD, there is a dot. That's the one thing. Maybe in my comment also it's included. Sorry. Just
so it is
CD
only
OpenWSN.
CD OpenWSN.
Yeah, CD OpenWSN.
OpenWSN. Yes. Okay. Thank you. Yeah.
Then, good. Then we are going to clone specifically the three repos. So one is with respect to OpenWSN firmware and OpenWSN visualizer and the CoAP. So now I'll share my screen. Try again. And share screen, entire screen. Okay. Okay. So okay. So I'm inside the OpenWSN directory and sorry. And I have the three required directories. So that's what I was telling. Like, and the three required stuff is like an OpenWSN firmware. So the first one is like an OpenWSN FW, that is with respect to the firmware. So this holds the firmware source code. The firmware source code which runs on the possibly emulated modes. So the modes can be, yesterday you may have seen like in one of the Sky mode, that can be like an Telos mode, or it's like an open mode, or it's like an so many different
Sir,
kinds of.
ಇವರಿಗೆ ಹೇಳ ಶ್ರೀನಿವಾಸ್ಗೆ ಹೇಳ ಕಾಫಿ ತರಕ್ಕೆ ಶ್ರೀನಿವಾಸ್ಗೆ ಕಾಫಿ ಶ್ರೀನಿವಾಸ್ಗೆ ಹೇಳ ಹಾ ಶ್ರೀನಿವಾಸ್ಗೆ ಹೇಳ್ತೀನಿ ನಿಮಗೆ ಎಲ್ಲಿ ಸರ್ ಮುಗಿಯುತ್ತೆ ಈಗಿನ ಶುರುವಾತ್
Okay. Thank you. So OpenWSN FW firmware. So the firmware, as I told, it's completely firmware source code. So it is consisting in Contiki, probably you may have seen there is a directory which consisting with respect to all the embedded devices that can be like an MSA430 or it can be like with respect to the ARM architecture, or it can be with respect to an STM32 architecture and all. In the same way, this will also is completely consisting with respect to the emulated modes device. The open visualizer, which is the one more second one, this open visualizer will be consisting of the software source code, which runs on our computer. So this software code is completely like a simulized one. And the third one is like an CoAP, Constrained Application Protocol. So Constrained Application Protocol, as we have discussed till now, this is like in this package like completely implements the Constrained Application Protocol, which is specifically developed from the ITF, that is an Internet Engineering Task Force core working group. And this particularly, it implements like an CoAP client and also like an CoAP server with arbitrary number of resources it consists. Okay, so let's start with this one, OpenWSN. And I just one more thing, I just want to make you sure that whatever that you have cloned, make sure that you have cloned it completely, it's an up to date, just to make sure that give the command like git pull, sorry, cd OpenWSN and git pull. So it's like you must and should get like an already up to date. So this will make sure that you have completely successfully cloned it very properly. If not, it will just clone it and it will keep updated. So another one is like an open visualizer. And the same command again is like a git pull. So just make sure that those who have executed all the command one shot, sometimes some commands may be if you may have missed while testing. So just make sure that you have properly executed all the commands and you are able to clone it very properly. So that is like an open visualizer, OpenWSN, and CoAP.
Sir, what is the password? Git pull, when I give that command, the cloning, so it is asking for the password. So what's the password?
Oh, okay. So then you must have like for cloning, you must like have a Git account probably. Okay, if you don't have, that's fine. That's fine. Just again, it's like in GitHub repository stuff. Will not just get into it. So we'll just ignore it.
Okay. Yeah. Authentication failed, I think.
Oh, okay, okay. Then no worries. Just ignore it and make sure that we have cloned it. You are able to clone it. That's good enough for now.
Okay. Okay, fine. Thank you.
Okay. Thank you. And once we have all these repository like an side by side from the Git, so we are good to go with and running the simulation. So the simulation like an OpenWSN simulation, since the firmware is like an really mean with respect to the real modes. So we are going to make use of a simulated one here. So, and also one more thing is here we are making use of a Python too. Some people will face an issue with respect to the Python version. So make sure that you have a Python, which version? I have like an Python 2.7.18. So, or else you will face an error as well during the execution. So that's the reason we have given a command. We have installed apt-get install python dev. That is the command. Okay. So though once you are already installed Python and everything successfully, so I'm just going to the simulation part straight away. So we can run the simulation, just means like by taking the software in the Open Visualizer, go to CD Open Visualizer. Open Visualizer. And there is a specific file called requirements.txt. So we need to install this one with a command called as like an sudo pip install requirements.txt. When you give the sudo, that is like an admin permission, sir. So whenever you give, it may ask for the password. At that time, your password is those who are making use of an instant config, the password will be user. So pip install. Okay. My system pip is also not installed in my system. This is my freshly I've installed the OS. That's the reason. I'm just sorry for that. Let me install the tool. Just give me 1 minute. Okay. So I don't have pip. Just give me a minute. Python. Just I'm installing in my system as well the required tools. Just discuss already. Okay, good. It is open WSN. Okay, so those are installed completely everything. So then just go to the folder that is called as an CD OpenWSN firmware. So in this firmware, so mainly to execute the scon script, so we will give the command as just give the command as like an scon. So and then in which board we are trying to execute. The board that we are giving here is an Python. So if we are making use of any specific hardware device, then we are going with like an, if it is like an Telos, we are going to give it as like an Telos-B, or if it is like a Sky mode, both it depends upon the name what we are giving it. If we give it as like a Sky mode, if it is like an open mode, we can give it as like an open mode. So the board at present, since it is a simulated one, we are giving as a command as like an Python scons space and the board which is equal to the Python and toolchain. To compile, we must need a specific toolchain. So toolchain will be an GCC and then OOS under the OpenWSN. This is an extension module. So I'll just give this command in the chat box as well. Just you can copy paste it. Scons. Oh, sorry. I don't have scons board is equal to the Python is the board and then toolchain, which is be specifically or to toolchain will be the compiler that we are going to make use, and there is an GCC yes underscore open WSN. So make sure that you will give this command, and once you after you giving this command, so you will get an output as like an open WSN. Just I will show that one. I know in my system it will throw an error. I'm just trying to set my other device. That's the reason. Just give me a minute. To debug this issue, it is very much time consuming. Yes. Okay, make sure that everyone have executed this command, and you must able to see specifically the output as like this. So that is with respect to scon, that then board is equal to Python, and toolchain just it is to compile and build the target files. So we are not executing, just we are building the compilation right now. So if anyone face an error as like with respect to the print statement, that is specifically with respect to the Python version. Just let me know if anyone are facing that issue. So we need to set up the Python file path. So if it is pointing to an Python 3, so then it has to be like in Python 2.7. So make sure that you will get an output as like an scons build targets. So actually, yeah, this step it will completely like an compile the OpenWSN firmware. as we are given the board as like a Python extension module. So this will completely build the simulation environment, and it will at the runtime, and it will keep it ready. Once you are completely able to execute that command, and if you are able to build the scons build target, so then our next command is like an just let me show scon run web and the simulation. Just let me show that. Okay, that is like an sudo admin permission scons run web space hyphen simulation. So now it will start with an showing as like an scons reading scons script files and open WSN. So make sure that you will get an output in the way what you are saying. Yeah, I'm supposed to execute in my system. I'm getting an error. I'm very much sure if I'm going to fix it, it's going to consume some time. Sudo space scons run web hyphen simulation. I hope everyone able to get that. And the last point is to, so if you are able to successfully run the simulation as we are getting here, so then it is to see the simulation visualization in the web browser. Just go to any of the browser. You can make use of an Chrome, or you can make use of an any of the other browsers as well. Yeah, open any of the browser like and then you must give the loopback IP address. That is like an 127.0.0.1 and then colon 8080 is the port number. I hope everyone following this. Just open your once you execute the simulation command, just go to the browser and give the command like 127.0.0.1, that is like a loopback address, and then colon 8080 is the port number. Since our simulation has started, so in our system in local machine, so we will get back the visualization in our web browser. Here, you will see some of the section called like modes, event bus, topology, routing, and documentation part. Documentation specifically with respect to the any nodes that we wanted to make up, and routing. This will show how the devices are connected with respect to the. Here also it will make use of an RPL routing protocol, and the topology. Which one is the parent and which one is the child nodes? The topology connected topology will be shown, and the event bus. The event bus is specifically with respect to the packet transmission. It will showcase. And here select modes and the toggle DAG root states. So here DAG root means this is like an DODAG destination oriented direct acyclic graph. In that one, the parent node. So that is like a gateway device. So you can choose this device can be the DAG device, DAG root device, or else you can choose any of the specific device, which one you want the device. You can choose the mode and you can make it as like a parent device. I mean the gateway device. Just try around that. Hope you all able to make it. And next part is like an click on the topology just to visualize the topology. So how the devices are connected apart. So in between the devices, it is prospectively. Let me show that part as well. Stage. Okay. You can see my screen. So in the topology, how the devices are connected. The first device, second device, and the third device. Here, the first device is our DAG route. So this DAG route is the device, which is the gateway device. So just I'm giving a time. Those who are still following it can make it. Okay. And then followed by the next two devices is like a second node and the third device. So if you look into the topology, the first device is a gateway device. The first gateway device for that one, the connected device is an second device as a child device, and for third device is another child device which is connected to the second device. You can just move around the devices as well. I just give some 2 minutes. Okay. So I hope everyone able to make it. Since yeah, I'm feeling bad since my system is giving an error with respect to the some path issues. So I just got stuck. So I'm just showing the snapshots that I have. Okay, with this, just play around, and I don't have much to. This is actually a really interesting part to play with and modes, to adding a number of modes and to include multiple modes into the network and to create a topology as we want. And the topology can be like an specifically, it can be like an two gateways, and we can change the topology as like in a multiple device. It can be like in 10 devices, 15 devices. We can create as well. And just mobility of the devices, which is very important. When there is a mobility of the devices, when the device move around, how the device connectivity will interchange, that can also we can verify here. So just play yourself, and if any issues are there, you can reach out to me in the offline. So just I would like to mention with that, and I would like to end up for this. So yeah, I would like to take up any questions if it is there, and also you can reach out to me offline as well for my email address.
Okay. The session is open for question. Participant can unmute and interact with the speaker, Mr. Adarsh.B.U. Okay, fine. I suppose there are no doubts as such. Mr. Adarsh.B.U, we shall have a valedictory function immediately following this concluding session.
Okay.
And we invite you to be the guest for the valedictory function.
Okay, sure.
And anyway, we'll be expressing our gratitude to Adarsh.B.U for taking time and effort again in this session. Thank you very much, sir.
Thank you so much.
We look forward for more of an interaction from your side.
Yeah,
And
sure.
for the participants, I'm sharing a link for the feedback on the session that has been just concluded. You please take time in filling up this feedback form, and we shall have the valedictory function in 2 minutes. Okay, may I request participants to turn on their webcams so that we can have a photo session, something like that. Will you all please turn on your webcams? Then okay, I'm sorry. Good afternoon. We'll just commence our valedictory function. The guest of honor is Mr. Adarsh.B.U, Director, EakTech. And it is a very short program in taking the feedback from the participants, as well as vote of thanks by Dr. Yogeshwari, Associate Professor in the Department of Electronics and Telecommunication Engineering. Before we take the feedback from the participant, we just look at, in retro, the webinar series that was arranged. It was scheduled over 3 days. On the day 1, we had Dr. M.H. Corey in giving the keynote address. Dr. M.H. Corey is in fact very closely associated with electronics and telecommunication engineering, being on the board of Department Advisory Committee. We are fortunate to have him as a keynote address speaker, and I suppose he has set the tone for the webinar series. The second session on day 1 was on MEC in context of 5G promises for IoT 5G algorithms by Mr. Abhijan Bhattacharya, and it went off well, keeping the interest of the participants for the subsequent sessions. On day 2, we had hands-on session both in the morning as well as in the afternoon. In the morning session, it was Mr. Adarsh.B.U touching upon cloud intelligence to edge devices with Azure IoT Edge. And hopefully, we as a research interested faculty got involved in the hands-on session and got benefited through the interaction with the speaker, Mr. Adarsh.B.U. In the afternoon session, Mrs. Soumya S. Vastrat was on the topic of exploring protocols in Contiki OS Kuja simulator, that also being a hands-on session. Then on the concluding day, that is today, we had a speaker from Finland, Mr. Mohit Sethi, who talked about research and standardization in IoT security. Finland, as he has mentioned, is labeled as the happiest nation in the world. I suppose the participants also got a feel of it in attending that session. The concluding session was again taken by Mr. Adarsh.B.U. It was on simulation of 6 TI SEH networks in the context of IoT. Though the hands-on session was a little bit short in time, still then probably he has generated enough interest in you to continue with the usage of simulation tools. Now, I have statistics and figures to be discussed with the participants. Being an international webinar series, we are happy to say that we have attracted interest among overseas nationals also. Almost 8 of them are from different countries. And as far as the participation composition is concerned, 15% of the participants are from the research interest, and the rest of them from the academia. So the very essence of arranging this webinar series, I suppose, has been attained. We had the interest of both the academia as well as the research scholars. Not but the least, Gender ratio, if you just look at it, it is almost 50 and 50% of male and female. So with that, we will move on to the first part of the valedictory function. It is about the feedback. We have identified 4 of the participants. I now call upon Dr. Prabhanjan, Professor, Department of CSE, Jyoti Institute of Technology, Bangalore, for a feedback. Over to you, sir.
Good evening to one and all. I thanks the HOD of Electronics Department, all the coordinators. Okay, for it was a very wonderful sessions, especially because I was especially computer science, but I was not in IoT and the IoT field. Especially this has given me some interest so that I can do some research in IoT also. Okay, thank you for giving me opportunity to attend this webinar, sir. Thank you.
Okay. Thank you, sir. And now I call upon Professor Yogeshwari Padani Swami from E-Road.
A very good evening to one and all present in the program. Really well organized with plenty of details in each session by the different speakers. Useful and practical session. This should be mandatory for anyone wanting to pursue research career. Thank you for organizing, and a special thanks to the speakers of all the sessions. Thank you very much.
Thank you, madam.
Thank you.
Now I call upon Professor Veena H.S., Department of ECE, Bangalore Institute of Technology, Bangalore.
Hello, good evening to all. This 3-day FDP International Webinar Series on research opportunities and recent trends in IoT and wireless sensor network, it was very, very informative and educative, especially for the research aspirants, which was started from Dr. M.H. Pori on 5G IoT recent trends, and also the second session, which was mobile edge computing devices by Dr. Abhijan Bhattarkar, and also hands-on session was very interesting on Azure software and simulate of IoT. Same day talk by Professor Soumya was very excellent, and today's session, both the sessions very, very informative. Thank you, sir, for all the speakers for this wonderful event. We expect more event and hands-on session from Telecom Department on embedded system. Thanks for this opportunity for me to talk about this. Thank you.
Thank you, madam. Now I call upon Mrs. Anupama H., Research Scholar, Department of ETE, BIT, Bangalore. Mrs. Anupama H. Okay. The platform is open for any of other 2 participants to give the feedback.
Good evening, everybody. This is Vadiraj from Jyoti Institute of Technology, Department of Information Science and Engineering. I take up this opportunity to thank BIT, the team behind this FDP. Thank you so much, sir. Me being a research scholar in the domain of IoT security framework, it really helped me, especially today's talk on standardization of IoT protocols. It really helped. It gave a different perspective. All these days we were talking about this conference papers, journal papers. Mohit sir gave us a different perspective on why not RFC. So we will seriously think about it. Thank you so much, Adarsh sir, also for that wonderful hands-on that we had. Thank you for the organizing team, because everything was properly organized. We had a lot of information before the hands-on started, right? It was a very active WhatsApp group that we had. All the instructions were given. I hope the recorded sessions are also already on the YouTube channel. Thank you so much, sir, this wonderful organization. Hope we have more such sessions in the future. Thank you so much.
Okay, thank you, Vadiraj sir. In fact, I was about to take your name because I was just going through the feedback given on sessions, and you have given us a feedback to say that you are trying to collect redundant information across different sessions like name, email ID, and phone number. Sir, very sorry for troubling you, but it was a necessity because across the sessions, a few more participants used to log in. In the context of collecting the data, those fields were added for every session like email ID, name, designation, and so on. Thank you. Thank you for your feedback.
Thank you for
Anyone
considering.
else? Okay, Anupama madam has logged in. Now I call upon Anupama madam to give the feedback.
Hello. Hello.
Yes, ma'am. Yes, ma'am. You're audible.
Hello. Thank you, sir. Thank you for a wonderful presentation. And it was really it helped us to gain knowledge on this subject. It was the whole presentation was nicely organized and it was good, sir. Thank you.
Thank you, ma'am. Now I request Dr. Yogeshwari, Associate Professor in the Department of Electronics and Telecommunication Engineering, to give the vote of thanks.
Yeah, good afternoon, everyone. Respected professors and the distinguished chief guest, Mr. Adarsh.B.U, respected principal sir, and our beloved HOD ma'am. It's a great honor for me to propose vote of thanks to all those who helped us in making this FDP a successful one. I would like to propose hearty vote of thanks to our chief guest, Mr. Adarsh.B.U, for handling the sessions and gracing the valedictory function. Thank you very much, sir, for your enlightening hands-on sessions and also for guiding us through organizing this event. Thank you very much, sir.
Thank you.
I'd like to thank our, thank you, sir. I'd like to thank our other distinguished speakers, Mr. Abhijan Bhattacharya, sir, Ms. Samya Vastrat, Mr. Mohit Sethi, and so I thank all the speakers for making the excellent presentations and making this FDP interesting and a meaningful one. I'd like to express our profound gratitude to our principal, Dr. Ashwath.M.U, sir, for encouraging us to conduct this FDP. I would also like to thank our beloved HOD ma'am, Dr. S. Shantala, for her moral support and her guidance. And I'm also happy to express vote of thanks to all our staff members who have made this FDP a success. And then during the FDP, we had the hands-on sessions. And I would like to thank our technical staff for helping us through this. And I also thank all our technical other staff members for making this event successful. And last but not the least, I thank all our participants for participating in this event, not only from our department, but also from other departments in our college, also from college and others and other countries as well. Thank you so much for your cooperation. Once again, I thank you all for your cordial cooperation. Thank you.
Okay, I suppose session is concluded. Thank you for your patience and time. Hope to see you in any of the other activities organized through electronics and telecommunication engineering. Thank you.